Hello everyone and welcome back to another video. Today we'll be taking a look at a British Informatics Olympiad question, and we'll be taking a look at the third question from the 2013 paper. So let's have a quick look at the question. Pretty much the question states that we need to find some sort of way to switch off all the lights in this particular sequence, and the way lights are switched on or off is that not only that light is switched off, but all adjacent neighbours are also switched off. So I'll let you have a detailed read of it before I explain it on the whiteboard. Okay. So I pretty much translated the problem into, if you see over here, how there are three possible states which lights can be off, dim, or bright. So I've represented the off state with 0, and the second state, the dim state, with 1, and the bright state with 2. So this basically translates everything into one of these three states. It can only be in one of these three, and it constantly cycles between these. So 2 would go to 0, 1 would go to 2, and then 0 would go to 1. So and now our problem becomes that we need to find some sort of way such that everything on here is just zeros. And the catch with this problem is that all adjacent neighbours are also impacted whenever a light is switched on or off. So it's not just as easy as switching on like certain lights. We need to have like some sort of proper plan. Now, the trick with this problem is that we need to notice for any light to be turned on or off, only one of the 5 neighbours or itself must have been turned on or off. So, for example, let's say I want to change this particular one over here. I can either change this 0, this 1, or this 2, or this 1 itself. Okay? Now, something which you may have thought of is that, well, okay, so as we can see, all of these current lights are switched like dimly, the 1, 1, 1, 1. So what if we were to just switch all of them twice? Then all of these would become zeros, right? So if we switch this one twice, it would become a 0. This would also become 0, and this would also become 0. However, the problem with this is that all adjacent neighbours are also impacted. So when we switch this twice, when we switch this 1 twice, then this one will also become a 0. And then when we try and make this one a 0, this will become like a 2 or something, and then it will just be a very big mess. So one of the key parts in the solution to this is realizing that it doesn't matter which order you switch on the lights. Because, for example, I could switch, like, in their example, they switched R, S, and T, right? I could do it the other way around, it wouldn't make a difference to the final answer. So that's part of where the solution comes from. And now, here's the crux of the solution. For any light to be, for any light which is switched on in the row above, we want to make that switched off. And we only want to make that switched off by altering lights in the row below. Okay, I'll just explain what I meant by that statement. So, pretty much, the issue which we faced with trying to make all the lights off within one row when switching adjacent lights on, was that we constantly were switching between on and off states. But then, let's say if we only switch off lights in the row below the lights which we want. So for example, let's say we want all of these lights in this row to be off. So what I'm saying is that we need to change lights only in this row, because then that will mean that only one light is accountable for this light being off. So let's say we want this off, we need to change this light by 2. So the way which we would do that is we would make the 2 over here. Instead of that 2, that would become 2 plus 2, and then that would become a 1 basically. And then this one would become 0. But now, also, since we switched this light on twice, we also impact all the neighbours. So instead of this becoming these zeros, those would become 2s. And then this one would also become, so these will become 2s, this one will become a 0. And now we can be sure that nothing can change the state of this light. Since this light has become 0 and there's no possible light which can change it, since we're only altering lights in this particular row. Okay? So now we just repeat this algorithm. So for this true, we need to make the light above it as a 1 into a 0. So we need to switch the 2 on twice. So then this 1 would become a 0, the 2 would become a 1, and all adjacent neighbors would also get switched on twice. This would become a 1, this would become a 0, and this would become a 0. And now we just repeat the algorithm. So we want this particular light to be switched on twice. So then what we would do is we would make all of these zeros. Sorry, that pen's not really working. But we make all of these zeros. And now we're done with this row, since all the ones on the third row are fully switched off. So now we go to the next row. So we need to switch this one on twice, so then this becomes a 0. So then the arrangement will become like this: 0, 2, 2. And then we will need to switch this 2 twice. And I'll show you the idea. We basically just repeat this, and eventually we will get some sort of arrangement where everything's a 0. So, and now you might be wondering, how exactly are we going to implement this code? So, an issue with the brute force approach here is that there are way too many possible combinations. Since, if we imagine, let's just go over here. So, there are basically 25 different cells. Each of those can be in either 0, 1, or 2 states. So then, if we were to just brute force all possible combinations, it would be 3, since all of these states to the power of 25, which is much bigger than like 10 to the 6 or 10 to the 7, which is the kind of limit of which programs can reach in 1 second. So instead of that, what we can do is we can basically alternate between certain. So instead of this brute force approach, what we can do is we only need to consider rows one by one, since for any row which is above the row, so let's say for this row to have all 1s, we need to change values on this row. So then our search only becomes 3 possible situations for each of the 5 elements within this row. Okay? So it becomes 3 to the power of 5, and then we do that 5 times, since we need to do that for each row. Now, at first glance, this might look the same as 3 to the power of 25, but it's not. This is much, much smaller. So this would be of the magnitude around 3 to the 7, which is like a very, very small number, basically. So now let's have a quick look at the code for this question. So I pretty much created this class, which is called lights, and this will have all the functions. The reason why I created a class is because these functions will be reused a lot, like within the code. So like a class is optimal for this sort of situation where you have multiple different functions interlinked. So the first thing which we're taking as input for the initialization of the class is the characters. These are basically the initial characters which are set. And this bit of code pretty much is just responsible for translating all the characters into the 0, 1, and 2. So if the character isn't mentioned in the input string, then it will basically be 0 since the light is switched off. If the characters are lowercase, then it will be a 1, and if the character is uppercase, it will be a 2. And we just repeat this for each character. And now we have this little bit of syntax. If you're not familiar with divmod, look it up, I won't explain it here, but this pretty much just ensures that each character has the appropriate row and column designated to it. Now we go to the second function, permutations. So as I was talking about, there are 3 to the 5 possible combinations or permutations for each row to be in, since each of the lights can be either 0, 1, or 2, i.e. switched on 0 times, 1 time, or 2 times, and that can happen for each of the 5 lights, so it would be 3 to the power of 5. So this just is generating all possible permutations of them, of the 5 different ones. There are more sophisticated ways to do this, but just for clarity, like this is the approach I chose, 5 for loops, and appending all possible permutations, then returning a permutations array. Now we have play. This is the main function, of the code, so I'll come back to them. I'll look at some of the other ones first. So we have update. What this does is, for any RC, any tuple RC, row column value, it'll basically update that particular value and its 5 neighbors. So this dy dx, nothing to do with differentiation, it's just the 4 adjacent neighbors. I just chose this code because it's quite easy to understand and clear. But this pretty much just tackles the neighbor directly below it, directly above it, east to it and west to it. And we iterate through all of them, and then we pretty much just increment the total, and then we do it more to 3. Since remember, 2 becomes a 0, 0 becomes 1, 1 becomes a 2. So this is kind of perfect for the modular arithmetic operators. And then of course we return the grid. And now we have check. So I won't go into this into detail, but what this pretty much does is it checks whether all possible. It checks whether the first row, which is passed as input, is made up of only zeros. If it's only made up of zeros, then we're basically done with updating the row below it. If you remember back to our whiteboard example. Excuse me. If a row is made up of only zeros, then we don't need to update the row below it any further. So in that case, it'll basically be returning a true, since if total equals 0, it will return true, as well as the copy of the particular grid which was passed to it. And over here, I'm just playing with the ASCII characters, since we're just converting the characters, converting the row and column positions back to their characters, since we need to maintain some sort of record of which letters have been pressed and how many times they've been pressed. So if they've been pressed once, then it's basically updating the lowercase. If the value is once, then it'll be updating the uppercase. Since if it's 1, then it'll basically be updated twice, right? So then it'll be the uppercase, and if it's 2, it'll be the lowercase. Since 67 and onwards, 65 and onwards for ASCII is the uppercase characters, and 97 and onwards are the lowercase characters. So that's what this function does. But now let's go back to the play function. This one's the most important within this entire code. So what this does is it iterates through each possible current row, and it takes as input a permutation of any such permutation, and it iterates through all possible permutations, and then it iterates through each of the column values, and then it checks whether that permutation will be valid. So what exactly do I mean by this? So a certain permutation, let's say 1, 1, 2, 1, 1. That means that you press the first one inside the row you're iterating over once, the second one once, the third one twice, etc. So it needs to check whether that particular permutation would result in all zeros for the row above it. And now if that condition is met, i.e. the row above it is met with all zeros, and the way we check this is we use our check function, which we've defined over here. If that condition is met, then we know that we're basically completed that particular row, and then we can move on to the next row, and so on. So that's pretty much how it works. This val is just updating the pref string, and the pref string is basically the store of all the possible characters, as I was talking about earlier, and a record basically of which cells have been pressed. And then we just iterate over everything. If res is the result of the check function, if that is true, then we will print the pattern since we're done, and then we will return out of this function. And then if at the end of this we don't have anything, then we just print impossible, since there's no possible permutation. And that's pretty much it, because then we just take a input string and we call the play function, and that's our code done. So now let's have a quick look at some of the sample test cases and see how our code does. Also, it's worth mentioning that in case you want to play around with the code or look at it in more depth, it will all be in my GitHub, which I will link for in the description below. So feel free to check that out. So let's just test it on maybe test case 7 here. this particular string. Our program basically is this. And now if we go back to the log scheme, and then if we control F for, okay, no, it's the field in here, LMR, that's right. And now maybe let's give it test case 8 as well. This is pretty much our output string. Now if we go back to the question, and then if we search for this particular string, it comes up over here. And now then let's just do one final test case, DHI. Go back to the program. And now if we search for where our data string is, it's over here as well. So that's pretty much it for this video. We've tested it on a few other some cases as well. I hope you enjoyed watching the video. Hopefully you learned something new about this problem. It was quite a creative one. So, and yeah, if you enjoyed watching the video, please be sure to leave a like and subscribe. And I hope to see you in another video next time.